Okay, welcome to this FMSP revision video for OCR FP3 on the topic of complex numbers. We'll start by looking at the specification statements and then look at some exam questions. So, there are 5 specification statements. The first of them is that you should understand how to multiply and divide complex numbers in terms of their polar form. Either r cos theta plus I sin theta or r e to the I theta. So if we multiply complex numbers, we multiply the lengths or moduli and we add the arguments, theta 1 plus theta 2. Similarly, if we divide the lengths, r1 over r2, and subtract the arguments, theta 1 minus theta 2. The second is an extension of this, which is de Moivre's theorem, which essentially says that if we were multiplying by the same complex number, in other words, raising a complex number to a power, so cos theta plus I sin theta to the n, that would be cos n theta would have n lots of the argument here, and I sin n theta n lots of the argument there. You should also understand how that can be used to solve standard trig problems in terms of multiple angles and similar type things that you might have met in things like C3 and C4. There are then statements for sin theta and cos theta in terms of e to the I theta, which we'll look at in detail in a second, and again solving those, using those to solve particular problems. And finally, the nth roots are unity, so you should know that if we're solving z to the n is 1, we're looking at the nth root of 1. Well, clearly 1 to the n is always 1, but there's complex numbers. There's actually n complex numbers, but if you raise them to the power n, you get the answer 1, and they're distributed at equal angles around the origin. Couple of things that will make those a bit clearer. These first two statements in terms of r e to the I theta aren't given in the formula book, so you are expected to know these. In practice, this first statement here is probably better and more easily remembered as cos theta is 1 over 2 e to the I theta 1 over e to the I theta, or e to the minus I theta, and we're adding them in the case of cos. For sine, you're subtracting them, so sine theta is 1 over 2i. Don't forget this I here, that's really easy to forget, multiplied by e to the I theta minus 1 over e to the I theta, or e to the minus I theta. You do need to learn these, they're not in the formula book. What is in the formula book is the statement of de Moivre's theorem, the statement in terms of the two alternatives versions of a polar form for complex numbers, and this final statement saying the roots of unity are, the I is not the key thing here, it's this term here is saying they're split evenly around the origin. So for example, if we were solving z cubed equals 1, we'd have a root at 1. There's actually going to be 3 roots split evenly around in an equilateral triangle that will look something like this on the Argand diagram. 5 roots will be split round in a pentagon. So let's take a look at some exam questions. We'll start with one that looks at this e to the I theta and e to the minus I theta form. So, reading through the whole question, you're asked to express sin theta in terms of e to the I theta and e to the minus I theta, and then, using that, show that sine to the 4 theta is an 8th cos 4 theta minus 4 cos 2 theta plus 3, and then secondly, use that to solve an integral. So, doing the first part to begin with, we should be able to write down sine theta is 1 over 2 I, remember, don't forget this I, e to the I theta minus e to the minus I theta. Once we've done that, we can use that to find what sine to the 4 theta is. So sine to the 4 theta is this whole thing raised to the power 4. So I've got my fraction raised to the power 4, and then I'm going to raise this bracket to the power 4. Now 1 over 2i all to the 4, 2 to the 4 is 16, I to the 4 is 1, so this fraction is just a 16th. And now what I've got here is, you don't need to write this down, but effectively I've got a binomial to the power 4. The row 4 in Pascal's triangle looks like 14641. So I'm going to expand this as a straightforward binomial, and I get e to the 4I theta minus 4 e to the 3I theta times by e to the minus I theta plus 6 e to the 2I theta times by e to the minus 2I theta minus 4 e to the I theta times by minus 3I theta, and then finally plus e to the minus 4I theta. Squeeze that bracket on the end there. Now what I want to do is collect these things together, and thinking about my version of cos theta in terms of e to the I theta, I can see I've got e to the 4I theta and then e to the minus 4I theta there. So I'm going to bring all those together. I also know that the cos terms have a half on the front, so I'm actually just going to split this 16th into an 1/8 times by a half. Then I've got my half on the front, and that leaves me e to the 4I theta plus e to the minus 4I theta. I've then got a couple of terms here, 4 e to the 3I theta times e to the minus I theta. That's going to come together into e to the 2I theta. So I've got minus 4 e to the 2I theta, and similarly from this one, minus 4 e to the minus 2I theta. And finally e to the 2I theta times e to the minus 2I theta gives all of this is 1. So that's plus 6. And I can bring all of that together now, and I get an 1/8. A half of this is cos 4 theta, which is what we wanted. A half of this is minus 4 cos 2 theta, and a half of 6 is 3. And we should feel a warm glow that we've got the expression that we wanted on the right hand side. Now the second part of the question just uses that to solve an integral. So I want to integrate from 0 to pi over 6 of sine to the 4 theta d theta, which is now going to be the same as integrating from 0 to pi over 6 of 1/8, which I'll stick out on the outside of the integral where it won't do any harm, cos 4 theta minus 4 cos 2 theta plus 3 d theta. I'll go through the rest of this fairly quickly because this is fairly standard A2 core work. So this is now an 1/8 of sine 4 theta over 4 minus 2 sine 2 theta plus 3 theta. Evaluated between 0 and pi over 6, and then if we evaluate that we get an 1/8 of root 3 over 8 minus root 3 plus 3 pi over 6, evaluated at pi over 6, 0 when evaluated at 0, and then just tidying up we get pi over 16 minus 7 root 3 over 64. So let's take a quick look at how the marks are awarded for this question before we move on. In the first part of the question there's a straightforward mark for the statement here of what sine theta is. There's then a method mark for being able to expand this in terms of a binomial to the power 4. A second method mark for grouping these things correctly, so you can see how you're going to get cos 4 theta out of it, and a final accuracy mark. And then in the second part of the question there's a method mark for a correct attempt at an obviously correct attempt at integrating, an actual accuracy mark for the integration itself, and similarly a method mark for what looks like a convincing attempt at substitution, and an accuracy mark for the final answer there. But you should see from that it's this new idea in terms of e to the I theta for sine, and then using that to solve problems that should look essentially familiar once we've done that. So let's take a look at a question that involves roots of unity. So again, reading through the whole question before we start, it says write down in Cartesian form the roots of the equation z to the 4 is 16, and then hence solve the equation w to the 4 is 16 1 minus w to the 4, giving your answers in Cartesian form. So this first part says write down, and we should know that our roots for z to the 4, well, clearly 2 is a root, and there's 4 roots distributed evenly around the origin. This should look like that. So in part 1 we should literally be able to write down z is 2, 2i, negative 2 and negative 2i. Part 2. Can we solve w to the 4 over w to the 4 is 16 lots of 1 minus w to the 4. I'm going to divide through by 1 minus w to the 4 to begin with is 16. Then I can take the fourth roots, and you can see how that's useful in terms of what we've done in part 1. So if I take the fourth roots at the left hand side, I get w over 1 minus w, and that can equal one of the following 4 values. And now essentially I just need to solve for each of these separately. So taking the first one, w over 1 minus w is 2. I get w is 2 minus 2w, 3w is 2, w is 2 over 3. Similarly, w over 1 minus w is negative 2. I get w equals minus 2 plus 2w. Rearranging all that round, I get here w is 2. w over 1 minus w is 2i. I get w is 2i minus 2iw. So 1 plus 2i w is equal to 2i. W is 2i over 1 plus 2i. I can multiply top and bottom here by 1 minus 2i, and I get w is 4 plus 2i over 5. If I follow similar through, for w over 1 minus w is negative 2i, I'll essentially get w is the complex conjugate of that, 4 minus 2i over 5. So in terms of the marking here, there's 2 marks for stating all of these correctly without any mistakes. Dropping 1 if you make a mistake. There's then a method mark here for identifying that this expression can equal any of these 4 right hand sides. A method mark for an attempt at solving the left hand side is one of the right hand sides. An accuracy mark for getting at least 1 correct. A further accuracy mark for both the reals, and a further accuracy mark for both the complexes. But again, it's following this theme of we've got a new idea, we use that to give us a statement, and then we can solve a problem that we would have been able to solve using maths that we already knew, in this case more FP1 style maths. So finally, let's have a look at de Moivre's theorem question. So in this question, we're asked to begin with use de Moivre's theorem to express cos 4 theta as a polynomial in cos theta. Then prove that cos 4 theta cos 2 theta is this expression. Then use that expression to solve cos 4 theta cos 2 theta equals 1. And similarly use that expression to solve cos 4 theta cos 2 theta is negative 1. Let's have a go at the first couple of bits then. De Moivre's theorem is based on cos theta plus I sin theta to the n. So I'm going to start with a statement, essentially de Moivre's theorem written the other way around, which is this is normally appearing on the right hand side. That's the result if we raise cos 4 theta plus if we raise cos theta plus sine theta plus I sine theta to the 4. I'm now going to write out what the whole of this right hand side is. In class you may have just gone straight to doing the real part, and that's fine if you want to do that here. I'm going to go for the full expansion of this. So I get, well, the other thing I'm going to use as a shorthand is cos theta, I'm going to use C, and sine theta S. This is fairly standard. You don't need to tell the examiner you're doing this, but you do need to give your final answer in terms of cos theta. So I get C to the 4 plus 4 C cubed times by IS. Then I'm going to have an I squared in this one, which is going to be a negative 1, so I get minus 6 C squared S squared. I'm then going to have an I cubed, which is minus I, so I get minus 4 C S cubed. And finally, I to the 4 is back to 1 again, so I get plus S to the 4. Now this is where I'm going to identify that what I want is the real part. Essentially, if I expand all this out, the real part is the cos 4 theta bit, so the real part of this is cos 4 theta. So I can now say my real part is C to the 4. I'm also, because I want to go into cos theta for my expression, I'm going to replace sine squared with 1 minus cos squared. Bit of standard A-level core maths there. So I'll say minus 6 C squared 1 minus C squared 1 minus cos squared. Similarly, S to the 4 is 1 minus cos squared squared. Sine squared is sine to the 4. Now I can bring all of those together, and I get C to the 4 minus 6C squared plus 6C to the 4 plus 1 minus 2C squared plus C to the 4. And I'm going to give my final answer in terms of cos theta. So I get C to the 4, 6C to the 4 and C to the 4. I've got 8 cos to the 4 theta. I've then got minus 6 and minus 2 is minus 8 cos squared theta and a plus 1 on the end. Hence prove cos 4 theta times cos 2 theta is this right hand side here for 1 mark. So let's have a look at part 2. This should be fairly straightforward. If I multiply cos 4 theta by cos 2 theta, I've got my expression for cos theta, for cos 4 theta, and I should know that cos 2 theta is 2 cos squared theta minus 1. Again, it's a fairly standard bit of A-level core you should be familiar with. Multiplying all of those out, I get a cos 6 to the term, which is 8 times 2. 18 cos to the 6 theta. Cos 4, I've got a minus 8, and a minus 8 times 2 is minus 16, a total of minus 24 cos to the 4 theta. For cos squared, I've got minus 8 times minus 1 is plus 8, and 1 times 2 takes me up to 10. And then my final term is minus 1. And again, I should get a warm glow that I've got the correct answer, and take that confidence on to the next part of the question. So, in part 3, you're asked to use part 2 to show the only roots of cos 4 theta, cos 2 theta equals 1, or theta equals n pi. I've copied over what it should be here, because that's what we're gonna use. So, but we are doing part 3 here. So I basically want to solve 16 c to the 6 minus 24 c to the 4 plus 10c squared minus 1 equals 1. Now I need to take that 1 over to the right hand side. Any polynomial, your immediate reaction should be to look at solving it equal to 0. So I get 16c to the 6 minus 24c to the 4 plus 10c squared minus 2 equals 0. Now we can take a factor of 2 out, leaving us 2 8c to the 6 minus 12c to the 4 plus 5c squared minus 1 is 0. Now you may feel a bit stumped here, but the thing to notice is this is a cubic in c squared. We've got a constant term, c squared, c to the 4, c to the 6. And you should be familiar with solving cubics from AS Core. So what we really need to do is look at, are there any values of c squared that work for this? Well, actually c squared is 1. We'll get 8 minus 12 plus 5 minus 1 is 0. C squared is 1 works, so c squared minus 1 is a factor, leaving us with 8c to the 4 on the front and plus 1 on the end, and our c squared term, well, we've got our c to the 4 term, we've got minus 8, we'd need another minus 4, so that gives us minus 4c squared. If you're unfamiliar with what I've done there, go back and look again at your AS Core stuff. I've just solved the cubic. The cubic happens to be in c squared, but I've just factorised the cubic to help me solve it. This then leads to two alternatives. Either c squared is 1, so I've got cos theta is 1, or cos theta is negative 1, and both of these happen at 0, 2 pi, 4 pi, 6 pi. These happen at pi, 3 pi, 5 pi, 7 pi. In other words, these happen for any integer times pi. Or here, I've got a quadratic in c squared, but I don't want this to give me any roots. Why wouldn't it give me any roots? Well, b squared minus 4ac, the discriminant, 16 minus 32 is less than 0. b squared minus 4ac is less than 0, so there's no real roots. Similarly, but possibly slightly easier, here we're solving the cos 4 theta, cos 2 theta is negative 1, so we're actually starting off with 16c to the 6 minus 24c to the 4 plus 10c squared minus 1 is negative 1. If I add that over, I get 16c to the 6 minus 24c to the 4 plus 10c squared is 0, and this is easier now because I can just take out a factor of 2c squared, leaving me with c to the 4 minus 12c squared, 8c to the 4 minus 12c squared plus 5 is 0. This only works when cos theta is 0. So we've got c squared equals 0, only happens when cos theta is 0. And again here, b squared minus 4ac, 144 minus 4 times 8 times 5, 4 lots of 40 is 160 is negative, b squared minus 4ac, 4 lots of 8 times 5 is 160, 144 minus 160 is negative, is what I should have said. And again, no real roots. Let's have a quick look at how the marks were awarded for this. So on the first part, there's a method mark for correctly expanding a binomial to the power of 4, and an accuracy mark if you get all your terms correct there. Then looking at the real parts correctly in terms of, and doing your 1 minus c squared is worth another method mark, and finally an accuracy mark for the answer. And obviously just 1 mark here if that's convincingly correct. It is a hence prove that question, so you do need to get this 2 cos squared theta minus 1 in for cos 2 theta for the mark. Part 3, there's a method mark for a correct factorisation, and then 2 accuracy marks for both of these 2 statements, and similarly a method mark for the factorisation and 2 accuracy marks for both of these statements here. So please look on the website if you want some videos for other topics on FP3 and also some videos for some other units.